Section 3.4 is going to be about piecewise defined functions. And we're going to need to use what we know about parent functions to be able to make these graphs. As you can see, a piecewise defined function has more than one rule that talks about its graph. This one has three different rules. So what we've got, this part of it is the rule that we're going to follow. And then this part over here is the domain for that rule, or the zone where that rule is going to be followed. Now, the domain for the entire function is going to be, like, you have to look at the whole thing once it's graphed, but this x is less than or equal to -2 is the domain for the rule y equals -x. Okay, so one way that I kind of like to get these started is to kind of color code my zones. So I'm going to get my axis split apart here. I guess I could have done this before I turned on the video, but I did not. Okay, so when x is less than or equal to -2, that's going to be the x-axis from -2, including -2, and going left, which means the entire part of the graph from -2 over is going to be in that zone. So I'm going to color that zone pink with my pink highlighter. I'm going to try and make it somewhat parallel to the y-axis. So from -2 to the left is all going to be that zone. Then my next zone, or the next rule, is going to be between -2 and +3. I'm going to make that one yellow. So between -2 and +3, we're going to be in this yellow zone that's going to follow the rule y equals 9 minus x squared. So we're going to get to graphing these here in a little bit, but first I want to get my zones colored in. And we're going to talk about the borders in a moment. This is going to be all kinds of stuff. And then the last zone that we're going to be using is when x is greater than 3. So that's going to be from x equals 3, everything to the right of x equals 3 over in here. Okay, now that we have our zones established, let's look at the functions that we're going to be graphing in each of those zones. So in that pink zone, we are going to be graphing, so this guy, I don't think that's fine. I'll just use this color. I wanted pink, but it's like brick red. It's fine. Almost looks brown. So this zone here is going to go from -infinity up to -2. Since it has that closed symbol, it's going to be a closed bracket like that. And the rule we're going to graph, so on this section, we're going to graph y equals -x, because that's the rule that goes to that zone. Well, what does that graph look like? It is going to be a line. The slope is -1, and the y-intercept is 0, 0. So we're just going to graph a line that has a slope of -1 and a y-intercept of 0, 0. But I'm only going to draw that graph in the pink zone. So it's like I would start with a y-intercept of 0, 0, but I don't get to graph that point because it's the wrong zone. I have to stay in the pink zone. So then I use my slope of -1, so up 1, left 1. I still don't get to graph that dot. Up 1, left 1. Now here's where I get to start graphing. So I'm just going to put a little dot there. I need to decide if that's going to be an open circle or a closed circle. So I look at my boundary, and that is going to be a closed boundary because it was the less than or equal to. So at -2, there is a closed circle, and that's the first place I start drawing my line. And then I just continue following the slope of -1, and I get to draw that line everywhere in the pink zone. So that would keep going beyond the edge of my graph paper. Then I'm going to look at my next zone, which is this guy here. And that goes from -2 with an open boundary up to 3 with a closed boundary. And on that zone, I'm graphing this rule. So I'm going to graph y equals 9 minus x squared, which is the same thing as -x squared plus 9. So that is actually a parabola from our parent functions with a reflection over the x-axis and a shift up 9. So I'm going to start from 0, 9, and then my pattern will be over 1, down 1, over 2, down 4, over 3, down 9. Now the trick is going to be that I have to stay in this yellow zone. So I'm going to go up 3, 4, 5, 6, 7, 8, 9. Since I'm in the correct zone, I get to put a dot there. And then I will follow my pattern over 1, down 1, and on the other side as well. And then over 2, down 9 puts me here. Over 2, down 9 puts me here. Now I'm right on this border. So on this border, I need to pay attention that this is an open circle, an open boundary. So on this ordered pair, it's going to have an open circle. Oh, I went down 9. What am I doing? Help. Send help. Down 4. 1, 2, 3, 4. Right here. Let's get that going. 1, 2, 3, 4. Right there. Okay. Wow. It's too early in the morning, apparently. So that's where my open circle is. And then go back to the original. Over 3, down 9 puts me right here. Now this one is a closed circle because on the border between the green and yellow, on the 3 end is a closed boundary. So it's a closed circle. So I'm going to draw my parabola just in the yellow zone. It does not keep going beyond those ordered pairs because that's the end of the zone. So that's the part my parabola gets to live in. And then I go to my green zone, and this green zone starts at 3 with an open boundary and goes to infinity. And on that zone, I'm going to graph the rule y equals x minus 3. And that, again, is a line with the slope of 1 and the y-intercept of 0, -3. So I'll go to my y-intercept of 0, -3. And I don't get to put a dot there because it's not the correct zone. So I just follow the pattern. I go up 1, over 1. I can't put a dot there. Up 1, over 1. I can't put a dot there. Up 1, over 1. Okay, I can put a dot there. But on that 3, it's an open circle. Well, I already have a closed circle there, so I'm just going to put my open circle kind of around it so you can tell that they're both there, and then move on. So up 1, over 1. Get a dot there because it's the right color. Up 1, over 1. And I would continue my line beyond the edge of my border because that goes to infinity. So this is what my piecewise defined function looks like. There's a couple of things that I really want you to notice and pay attention to. One of those things is that this is still a function. In other words, this graph passes the vertical line test. There's no point on here where if I run a vertical line, it's going to intersect two ordered pairs at the same time. See, I have a closed circle here, but an open circle here. Nowhere on here does it cross that vertical line twice. So notice that it passes the vertical line test. If your graph does not pass the vertical line test, something is wrong with your piecewise defined function. So be thinking about that. All right, let's talk about domain. So each individual part of this function has a separate domain. But if we look at continuing that domain across from negative infinity to infinity, we go from negative infinity to -2. We include -2. So that -2 is included. We go all the way to 3. We include 3. That 3 is included. We go to infinity. Looking at the graph, I have x values starting at negative infinity. And here at 3, I include 3. I pick back up. I go to here. Excuse me, -2. I'm including 3 as well. So the domain for this graph is negative infinity to infinity. Because it's continues all the way through without skipping any of the x values, it just changes where the graph is drawn. The range for this graph, if we scan from the bottom to the top, that's the range. That's the range. The lowest y value we have is 0, and we keep going. Now it looks like, if I didn't see this part of it, it looks like it skips some y values, but it actually doesn't, because they're still included here. So my y values keep going and, in fact, go towards infinity. So the range is going to go from 0 to infinity, and it includes the 0 because I have a dot right there. What about the intercepts on this graph? When I look at the graph, I can see where the x and y intercepts are. So here, there's a y-intercept that was at 0, 9 from graphing the parabola. And x-intercepts, I only have one right here at 3, 0. Now, if I didn't have the graph to look at, if I just had the rule to find the intercepts algebraically, then we'd have to deal with that slightly differently. So let's step through that. Remember, to find an x-intercept, what we're going to do is sub in 0 for y. And to find a y-intercept, we're going to sub in 0 for x. Okay. We would have to look at each of the different rules. So we'll start with our rule number 1. So our first rule was y equals -x. And remember that was on the interval for x is less than or equal to -2. Or negative infinity to -2. Okay. So let's find the x-intercept. We'll sub in 0 for y. So we'd have 0 equals -x, which gives us x equals 0. So that x-intercept would be 0, 0. However, if we look at our domain here, from negative infinity to -2, x equals 0 is not in that interval. So we would not include that as an x-intercept. When we find our y-intercept, put in 0 for x, we get y equals -0, so just y equals 0. which would be 0, 0 as well, and that is not going to count. It's the same ordered pair. Okay. Our second rule, which was in this yellow zone, was, so second rule. Our second rule was y equals 9 minus x squared. And that was our yellow zone, which was for -2 is less than x is less than or equal to 3, which was -2 to 3 as an interval. Okay, so let's find our x-intercept. So we sub in 0 for y. So 0 equals 9 minus x squared. That actually factors to 3 plus x, 3 minus x, which gives us x equals -3, x equals 3. So those ordered pairs would be -3, 0, and 3, 0. But we want to look at our domain here between -2 for x and +3 for x. So this -3 is outside the domain, so it's not going to count. 3, 0, the 3 is included, so 3, 0 is going to count as an intercept for this function. Now let's look at our y-intercept. So we sub in 0 for x. The y equals 9 minus 0 squared. The y equals 9. So that gives us a y-intercept of 0, 9. Let's check our domain. X equals 0 is in that domain. So 0, 9 is going to count. And then our third rule, which was y equals x minus 3. And that was our green zone, which was x greater than 3 or from 3 to infinity, not including the 3. Okay. Let's check our x-intercept. So we're going to sub in 0 for y. So 0 equals x minus 3, which would give us x equals 3. So that is the ordered pair 3, 0. Looking at our domain, 3 is not included in this interval, so this x-intercept would not be counted. For our y-intercept, so we plug in 0 for x, y equals 0 minus 3, so -3, which would be the ordered pair 0, -3. And the x value of 0 is not included in this interval, so that intercept would not count. So actually on this particular piecewise defined function, both of our intercepts came from that second rule. We can also evaluate this function for different x values, but we're not going to actually plug that number into all 3 of the rules. We just need to look at which interval each one belongs to. So if we look at our 3 zones, okay, I'm just going to draw a little mini zone here. Our first zone went from -infinity to -2, and it included -2. Our second zone went from -2, but didn't include -2, over to 3 and included 3. And then our third zone went from 3, but didn't include 3, over to infinity. Okay. So when we are asked to evaluate a function, what we want to do is look at where this x value lies within our zones, and then we'll only substitute into that particular zone. So looking at f of 5, 5 would be over here in this green zone. So what we're going to want to do is only substitute into the rule that goes to the green zone. And that rule was y equals x minus 3. So I'm only going to substitute 5 into y equals x minus 3. So we do f of 5 would equal 5 minus 3. So that would be 2. And then I'll do the same thing here when they ask me to find f of 2. So f of 2 is going to be in this zone between -2 and 3. It lives in that zone. So I'm only going to substitute x equals 2 into the yellow zone function, which was y equals 9 minus x squared. So f of 2 will equal 9 minus 2 squared, so 9 minus 4, so that will give me 5. Just make sure that when you're substituting these values in, you only sub them into the zone that goes with their rule. On this one, we didn't even use that first rule, y equals negative x, because we weren't asked for any x values that were in that zone. Okay, let's practice another little piecewise defined function here. So remember that we've got our rules in that first little section. So these are our rules. And these are our zones or domains. Okay. So let's set those up. I'm going to do that similarly to how I just did it a moment ago. So the first zone is going to be x is less than -1. So that corresponds to an interval from -infinity to -1, not including -1. And we're going to graph the rule y equals -1. Then in my next zone, which is here, that corresponds to an interval from -1 to 1. And I have a closed circle or a closed bracket on the left end, but an open on the right end. And I'm graphing this rule. So graph y equals 1. And then my third zone here, x is greater than or equal to 1. So that is going to be an interval from 1, which includes 1, to infinity. And I'm going to be graphing y equals 2. So all three of these are actually horizontal lines. And we would want to make sure we pay attention to the open and closed circles on the ends of those lines. So let's go ahead and get our zones color if you want to color them. You certainly don't have to. I am going to color mine. So if you want to pause and color yours, come back and check. Here are my colored zones. And on each zone then, I'm going to graph the rule that goes with the zone. So on the pink zone, I am graphing y equals -1. That's a horizontal line at y equals -1 down here. So normally we'd have, all the way across, but I can only draw that in the pink zone from -infinity to -1. And this here means that we're going to have an open circle at the borderline. So I'm going to have an open circle here and then graph that horizontal line going to the left. Then that yellow zone, y equals 1. That's a horizontal line up here at 1. Pretend that's not there. but I can only graph it in this zone. And then paying attention to the borders, I have a closed border on the left end, an open border on the right end. So closed here, over to open here. And then in my green zone, the rule is y equals 2. So a horizontal line up here at 2 with a closed boundary right there, and then continuing forever. So here's my piecewise defined function. Let's look at the domain. So domain, again, if we scan left to right, the first x value I hit is this arrow, so negative infinity. I get to right here, and that x value of -1 is covered, but it's not double covered, so it's still a function. So it's covered, and I get to the next spot here, and the x value of 1 is covered, but not double covered, still a function. Keep on going, keep on going, keep on going. So that domain is negative infinity to infinity. Then the range. As we scan the y values, starting at negative infinity, no y values until -1, and then we skip a bunch until we get to 1, and then we skip a bunch till we get to 2, and then there's no other y values. So I've seen people write their range like this. So from -1 to 2 are the only y values that are included, but that would mean we have every ordered, like every y value between -1 and 2 covered, and we don't. So we cannot list our range like that. The range actually only has 3 values. So that range would just include -1, 1, and 2. The most appropriate way to do that would probably be in set builder notation or just set notation, because we can roster, like we can list each y value in a roster rather than in an interval. Intercepts. So x and y intercepts. We have no x-intercepts. The only intercept we have is this y-intercept right there at 0, 1. They're asking me a new question. Is it continuous? So let's talk about what we mean by continuous. A continuous function has no jumps, no gaps, no holes. This is not a technical definition. There is a much more mathematical definition for continuous, but this will work for our purpose. I've also heard people say that you can trace it from end to end without lifting your pencil. Pencil. I can't spell pencil. We got it. Without lifting your pencil. So if I jump on at the left end and I get to here, I have to lift up my pencil to go to here. I have to lift it up again. So this function is not continuous. Let's look at our previous function. Is this function continuous? Well, I go from here to here. I have to pick up my pencil, go to here. I wouldn't have to pick up my pencil over here. So in this section, it would be considered continuous, but because of that, it's not continuous. And neither is this one that we just read. Okay. All right, greatest integer function. This is also called the integer floor function. In the graphing calculator, it's listed like this, int, and I'm pretty sure it's in the math menu. Another symbol to use is this that looks like 2 capital L's, but like this one's facing in backwards. And I really like this visualization because it kind of looks like what it does, which is it takes the input and then drops it down to the next lowest number. So like 3 would stay 3 because if I drop it down to its next lowest number, it's still like 3. 3 is the next integer. 3.1 drops down. So 3.1 drops down to 3. 3.9 drops down to 3. 3.9999 drops down to 3. But 4 stays 4. So when I go to graph this function on the axis, if I go over to 3, that value is 3. 3.1 is still 3. 3.2 is 3. 3.3 is 3. All the way to 3.9 is still 3. All the way to 3.999. But as soon as I hit 4, it jumps. So I'm going to do an open circle on 4 because right at 4, it's going to jump up to the next number. So this pattern just repeats itself. So in between 2 and 3, at x equals 2, the value is 2. At x equals 2.5, still 2. 2.9, still 2. As soon as it hits 3, it jumps up. So this is what that graph looks like. Every value between 1 and 1.999999 is 1. So we look like that. Every value between 0 and 0.99999 would drop down to 0. So we go like that. And that pattern continues. So let's look on the negative values. The negative x values are the most challenging, I think. Everything between 0 and negative 0.99999, or excuse me, everything between negative 1 and negative 0.000001 would be dropping down to negative 1. Everything between negative 2 and negative 1.00001 would drop down to negative 2. So these drop down still. Negative 1 stays negative 1. Always like your integer values, they just stay the same. Negative 1.1 is going to drop down to the next integer. The next integer below negative 1.1 is negative 2. The next integer below negative 1.9 is negative 2. The next integer for negative 2 is going to stay negative 2. So that's what that integer floor function looks like. Okay. Oh, we need a graph on a calculator. So I'm going to have to get my calculator. I'm going to pause you for a second. Okie dokie. So to graph a piecewise defined function on a graphing calculator, we are going to have 3 separate rules for the 3 different zones. So the ones that have the double or the compound inequalities, you're going to have to use 2 different zones on that one. But the ones that just have a single inequality, you're just going to have to use 1. So let me get my stuff here. Okay, so in y1 equals, let's see, I wonder what color mine are. Okay. Maybe I'll change this color here. Okay. So I am going to graph in y1. That's going to be my first zone here. So y1, I am going to put y1 equals, and what I have to do first is give my rule in first parentheses. Kidding. I have to give my zone in my first parenthesis and then my rule in my second parenthesis. So I'm going to put the zone, which was x is less than or equal to negative 2. And then in my next parenthesis, I'm going to put, I don't type y equals, I just type negative x. Okay, so let's see what that looks like. So in y1, I'm going to put a parenthesis. The parentheses are above the 8 and 9. Okay, so let's write where things are located over here. So the parentheses are above 8 and 9. Like the parentheses are actually keys. You don't have to do second or anything for them. And then I need to type x is less than or equal to negative 2. So x is the regular x, and then less than or equal to, so the inequality symbols are in the test menu. And to get to the test menu, it's right here. It's that the white word. It's white on mine. I think it's probably blue on yours. We're going to have to push the second button and then the math button. So I'll do second math, and I need less than or equal to, less than or equal to. So x less than or equal to -2, and then close my parenthesis, open another one, -x. Make sure when you're using your calculator that you use the symbol for negative, not the subtract symbol. All right, when I have this double inequality here, I have to put 2 rules. I'll make that orange. Okay. So in my second rule here, this is going to be y2. So for y2 equals, if I have that double inequality, I have to do 2 zones. So I'm going to do zone, zone, rule. Okay. So my first zone will be, cover up this part, x is greater than -2. So I'll have x greater than -2. Then my second zone, x less than or equal to 3. And then the rule I'm following is y equals 9 minus x squared. So I just go 9 minus x squared. Okay. So let's try that. So in y2, I'm going to put parenthesis, x, get that test menu, greater than -2, close the parenthesis, next parenthesis, x. Whoops. Oh no, I deleted it. X greater than -2. Boy, did it. Okay, next parenthesis, x less than or equal to 3, and then parenthesis for the rule, 9 minus x squared. Okay. Then in y3, again, I've got only one inequality, so zone, rule. So my zone is going to be x greater than 3. My rule is y equals x minus 3. So I just put x minus 3. Okay. So my last rule, x is greater than 3. And the rule, x minus 3. Okay. Then I'm going to go look at my graph. So I'm going to do zoom standard. And I might want to do zoom square. Oh, we got a problem. I'm not sure why it's doing these graphs down here. I'll have to take a look at that in a moment. But here is the piecewise defined function. And it should look like our one that we drew by hand because it's the same function. So there you go. If you want to graph on your calculator, you can do that to double check what you're graphing by hand. But make sure that you know how to graph these by hand, since when you take your test, you're going to be graphing them by hand. So practice on graph paper and double check electronically if you want to. Okay, I just found a second way to type these in your graphing calculator, but it's only if you have like this fraction menu. So we're gonna type it in so that it looks like this, where we have our rule in the numerator and our zone in the denominator. Okay, so I'll show you how to do that. So to get the fraction thing, you're going to push alpha y equals. And then we're going to select numerator, denominator. So select number 1. And then in the numerator, we type the rule. And in the denominator, we type the zone, x. We still get the inequality symbol the same place. So x less than or equal to -2. And then we'll go in the second one. So remember, to get the fraction thing, alpha y equals, enter. And we type the rule, 9 minus x squared. And then test, we got to do x first. Oops, we got this. X is greater than -2. And then we need this word and. The word and is in that test menu, but we have to arrow over to logic. So I'm going to push the test menu, which remember was second math, and then arrow over to logic. So arrow over, and then there's the word and then x is less than or equal to 3. So test less than or equal to 3. Okay. Then in y3, again, we need the fraction, alpha y equals, choose the fraction, put the rule in the numerator, x minus 3, and in the denominator, x is greater than 3. And then when we push graph, this one comes out much more neatly. It doesn't have that extra lines down on the axis. But again, it's only going to work if you have that fraction-y menu, I think. I don't know. I'd have to play around with it. If your calculator doesn't have that, bring it in and maybe we can find a different workaround for it. Anyway, I just thought I would share that.